Norman Wildberger. Today we're going to look at the interesting and controversial topic of parallels in hyperbolic geometry. Now, the study of parallels was a key historical motivator for the discovery of hyperbolic geometry, and it's a consequence of trying to understand Euclid's fifth postulate. And in the 16th century, 17th century, 18th century, 19th century, people spent a lot of time and effort trying to prove this parallel postulate. Now, my point of view on this is that this entire episode is a study in misunderstanding and confusion. And it's really a red herring, a huge red herring in the history of mathematics. This is rather a minority opinion, as you can imagine, but nevertheless, there's a lot to be said for it. Now, in my Math History 12 lecture, which is entirely on non-Euclidean geometry, you can see some of my opinions on this subject. So please have a read or watch of this Math History video. So what is Euclid's parallel postulate, postulate number 5 in his book, The Elements? Well, it was that if you have a line L and you have a point P, which is not on the line L, then there's exactly one line through P which is parallel to L. So given L, given P, there's exactly one line through P which is parallel to L. And what does parallel mean? Well, according to Euclid, it means that these lines never meet, even if you extend them indefinitely. So Euclid's approach to lines was you always wrote down or drew a line segment in the plane, but you allowed yourself to continue that line segment, perhaps by extending the page. So to determine whether these two lines were parallel, Euclid would have had to extend the page and extend the lines, keeping on going and going and seeing whether they ever meet or not. Now, there's serious objections that ought to be raised to this definition. Okay? It's kind of obvious that this is not really a very solid definition, because how are you ever going to check that, say, these two lines are in fact parallel? It's possible to check that they are not parallel by extending them and finding out that those extensions meet. In that case, you could say they're not parallel. But if they happen to be parallel, how could you ever determine that? You're not capable of carrying on indefinitely. You can go for a mile or two, or maybe even a couple of tens of miles if you have inclination. Or theoretically, maybe you can go a few light years if you allow yourself to extend into space. It becomes a thought experiment. But even after you've done that, you still don't know whether the lines are really parallel or not. So this is a definition that really should have been brought under careful scrutiny. Okay, so people tried to prove this parallel postulate as a consequence of the other postulates, and eventually Gauss and Bolyai and Lobachevsky in the 19th century started realizing that there might be another geometry, which is a lot like Euclidean geometry, in which this parallel postulate does not hold. And eventually, when they discovered the various models of hyperbolic geometry, the Beltrami-Klein model or the Beltrami-Poincaré model, they could see that this parallel postulate didn't hold. So in the Beltrami-Klein model, for example, there would be a line L. There's a point P not on the line L. In this model, the line is only this line segment inside the disk. Now it's clear that there are a whole bunch of lines through P which do not meet L. In fact, there are sort of two limiting such lines. As you get closer and closer and closer, eventually you get to a line here which is exactly meeting the given line at this circle at infinity. And similarly, in the other direction, there's a kind of an extreme line that meets the line L at the other end at infinity. So in the standard hyperbolic geometry that you learn in courses and that's described in textbooks, very much is made of this. You know, that there are some lines which are not parallel and some lines which are, ultra parallel or super parallel or something like that. The Poincaré model is much the same, except that lines are more complicated to deal with. Lines are arcs of circles, like this one here. That might be the line L, a point P. Then again, we can see, analogously, that there are lots of lines through P. So other arcs of circles perpendicular to the boundary that don't meet the line L. And there are sort of two distinguished ones, that one and that one, which meet L sort of tangentially at infinity. All right. This whole discussion is a red herring, as I've said, and it's important to realize that one has to really take a step up from this discussion of parallels. So let's do that now. Even in Euclidean geometry, things are clarified by being more careful and more reasonable about what the notion of parallel means. It's always definitions which are at the heart of problems in mathematics. It's because people don't have the right notions to begin with that the theorems don't fit together properly. So in Euclidean geometry, there's at least two better ways of thinking about parallel lines. One of them is purely algebraic. If we think of a line as represented by an equation, say a1x plus b1y equals c1, and let's say another line L2, a2x plus b2y equals c2, then we can define what we mean by those two lines being parallel by this rule. We can say that they're parallel precisely when a1 b2 minus a2 b1 is 0. That's an algebraic, completely unambiguous definition of what parallel means. A geometrical definition, which is far superior to the other one, is this one. Suppose we have a line L1 and we have a point P. And we want to know what does it mean for the line L2 to pass through P and be parallel to L1. Well, what we can do is this. We can drop a perpendicular from P to L1. Okay, let's call that, say, N for normal. And then through the point P, we can drop a perpendicular to the line we've just created, to N, forming this line. In other words, parallelism can be constructed by two perpendicularities. So in Euclidean geometry, we could define parallelism of lines by this construction. However, there's an important thing that you need to check here in order for this discussion to make sense. In order for us to be able to ambiguously say that L1 and L2 are parallel using this definition, we need to check that it doesn't depend on where the point P is up here. So instead of the point P, suppose we have a point Q, and we drop a perpendicular from Q to L1. Is it still true that L2 is perpendicular to that normal? This is really equivalent to the existence of rectangles, of configurations of 4 points where there are 4 right angles, or 4 perpendicular lines. If we have such a thing, then this notion of parallel is unambiguous and well defined. Note that this approach is a local one, in the sense that you don't need to make measurements very far away from the point P in the line L1. Given the point P, given the line L1, to construct this L2, or to check that this is parallel to this, we just need to make a measurement here and a measurement here. We don't need to concern ourselves with what happens to those lines very far away or infinitely far away, which doesn't really make sense, does it? Okay, so we're going to take this definition to heart here, and we're going to look at similar approach to parallelism in hyperbolic geometry motivated by this picture. So here we are in our universal hyperbolic geometry setting. Here is a line L. It can be arbitrary. Here's a point A, which is, say, not on the line L. Let's think about what happens if we repeat the construction in the previous slide to this line L and this point A. One thing that we can do is we can drop a perpendicular from A to L. In other words, we can construct the altitude from A to L. How do we do that? Well, we find the dual of the line L, which is some point down here, say little l, And we just join A with little l. That line there, then, will necessarily be perpendicular to L because it goes through the dual of L. So that's our normal capital N. And it is A joined with L perp. Now we're going to construct another line through A which is perpendicular to N. Exactly in the same way. So how do we do that? Well, the dual of this line is some point over here. It's little n. It's the dual of this line here. So it's A perp times the dual of this, which is L. Then we take that point N and we just join it with A. That line there, because it passes through the dual of this line, will necessarily be perpendicular to it. And this line P is the line that we're going to call the parallel to L through A. So given L, given A, this is the construction for a line P called the parallel to L through A. And in terms of an explicit formula for it, here it is right here. We've joined A with little n, so it's A times A perp L. There's n, there's A. The join of those 2 points makes that parallel P. Now note, very important point. This construction depends both on the line L and the point A. So we do not say that this line P is parallel to L. That particular sentence we do not use in hyperbolic geometry. Cast it away forever. We never say one line is parallel to another line. What we do say is that one line is parallel to another line through a point. We need to say this point A because if we don't say this point A, it's ambiguous. For example, if we repeated this construction with A being replaced by the point B there, well then we would get a different parallel through that point, not the same parallel P. So it depends on L and on the point A. This is the notion of parallel that we're going to use in universal hyperbolic geometry. And it's going to serve us very well. It's a very important concept. So we're going to be interested in applying parallels to a triangle. To motivate that, let's go back to the Euclidean case. Suppose A1, A2, A3 is a Euclidean triangle. Then one thing that we can do is we can draw parallels through each of the points parallel to the opposite side. So this line we can construct parallel to that side, this line parallel to that one, and this one parallel to that one. Well, we get a very familiar situation here. Then by similar triangles, or the fact say that this is a parallelogram, this is also a parallelogram, it's easy to see that this segment is equal to this segment. So that this is actually a midpoint of that side. So A1, A2, and A3 are the midpoints of this side, and this side. And this bigger triangle, D1, D2, D3, that we've constructed from A1, A2, A3, might be called the double triangle of A1, A2, A3. Or in the literature, it's usually called the anti-medial triangle. But we're going to prefer the term double triangle. Okay, so that's a very familiar construction in Euclidean geometry, and it's the case then that this triangle here is the median triangle of the big one. It's just the triangle formed by the midpoints of the sides of the bigger triangle. We want to mimic this now because in hyperbolic geometry we now have a notion of what it means to draw a line through a point parallel to another line. So we can make the same construction in hyperbolic geometry. And it's quite interesting. So here's the picture. Given a triangle A1, A2, A3, say our standard triangle number 1, that one right there, we can construct parallel to the lines of that triangle through the opposite points. So through A1 we construct the parallel to this line here. So how do we do that? Well, first we have to construct a normal. We do that by finding the dual of this line somewhere here and then connecting it up with A1, that's the normal. And then, given that normal and this point, we construct a new line, this one here, which is perpendicular to the normal. Namely that it goes through the dual of the normal. That's how we get this side of our double triangle. Similarly, we get this side by going through the point A2 parallel to A1, A3, and we get this side going through A3 parallel to A1, A2. And you can check, and you should check, that this double triangle looks something like this. And we're going to give it a name. We're going to call it D1, D2, D3. So that D1, say, is the meet of the two lines passing through A2 and A3, and so on. So D1, D2, D3 is going to be called the double triangle of A1, A2, A3. So given any triangle, we can now create a double triangle formed from parallels to the original triangle sides through the opposite points. So here's how it looks algebraically. Using our standard triangle number 1. Here are the points of that standard triangle. I hope that's a little bit familiar to you. A1, A2, A3. And here are some computations that we've made earlier. Here are computations of the 3 altitudes. For example, N1 is 49 to 74 to 15. So how would we calculate the parallel, say, P1? Well, we need to join A1 with the dual of N1, the dual point to N1. Well, getting a dual point to this line is easy. You just change the round brackets to the square brackets. And joining is just a question of the j function. So we just need to take j of the coordinates of A1 right there and the coordinates of N1 right there. And when we do that, we get this value for this parallel line, minus 325 to 290 to 369. And similarly, P2, that line there is there. P3, that line there is there. You can check those calculations for me. Now what about the actual double triangle, D1, D2, D3? To find those points, we need to find meets of these parallel lines. So for example, to find D1, we need to find the meet of P2 and P3. There's P2, there's P3. So it's another j function. It should actually be a little j because officially the little j outputs a point, the big J outputs a line. So the values, of course, to the two j functions are the same. So we take j of this triple, and we get D1 being this value here. D2 that one, D3 that one. That's the double triangle D1, D2, D3 of the original triangle A1, A2, A3. And now we come to the main theorem of this lecture, which is, to me, very surprising. I was bowled over by this theorem. It is the double triangle midpoint theorem. It asserts that if D1, D2, D3 is the double triangle of A1, A2, A3, then in fact A1, A2, and A3 are midpoints of these sides D2, D3, D1, D3, and D1, D2 respectively. In other words, there's our double triangle. A point like A3 is actually the midpoint between these two points here. And that means that the reflection in this point actually sends D1 to D2 and sends D2 to D1. So that's the same thing that's happening in the Euclidean, much simpler situation. But somehow I felt that there was no real good reason why this should be. And in fact, still I don't have really a good reason why this is, to be honest. It's still a rather extensive computation. It's just some kind of miracle that seems to happen. Maybe some of you can deduce a simple reason why it might be, but I do not know of such a simple reason. And here's another pleasant theorem concerning this double triangle. The double triangle perspective theorem, which says that the double triangle is perspective with the original triangle. That means that if you join A1 with D1, and A2 with D2, and A3 with D3, those three lines meet in a point, center of perspectivity. And we're going to give that a name. We're going to call that the X point of the triangle, or the double point of the triangle A1, A2, A3. I'm going to denote it by X. By the way, Desargues' theorem applies here because we have two triangles which are in perspective. So Desargues' theorem says that if they're perspective via a point, they're also perspective via a line. So I'll leave it to you as an exercise to see if you can figure out what that line is. It's also a line that we've seen before. So this is a new point in triangle geometry that we haven't got so far, the X point of a triangle. And in any given situation, we can compute this X point very explicitly, again, just by using the J function. So in our standard triangle 1, where we know what A1, A2, A3 are, we know what D1, D2, D3 are, we can compute these lines joining the corresponding A's and D's, and then we can compute the joins of two of them to find that X happens to be this, 195 to minus 97 to 485. I'll leave that to you as an exercise. And I remind you that here is the orthoaxis of that particular triangle, which I claim is the most important line in hyperbolic triangle geometry. And you can check that the point X actually lies on the orthoaxis. To do that, you need to check that this times this plus this times this minus this times this is 0. It's an integer calculation. You can do it. There's the point X on the orthoaxis. I've also shown you the orthostar, which I hope is familiar, the orthocenter, H, and the base center, B. And it turns out that those 4 points have a certain fixed cross ratio of 3/2. So in particular, if you know where 3 of those points are, you can calculate where the 4th one is directly. So we can start with a triangle and create the double triangle. But why not create the double triangle of the double triangle? We can do that. And we get the second double triangle perspective theorem, which says that the double triangle of the double triangle is perspective with the original triangle, say A1, A2, A3. So here's the picture, again a little bit magnified down now. There's the original triangle A1, A2, A3, still the standard triangle number 1. There's the double triangle that we've been talking about. And now the double triangle of this double triangle turns out to be this one right here. As an exercise, you can calculate this double triangle. And what the claim is that this double triangle, this one here, is perspective with the original triangle. So if you join corresponding points, this one to this one, and this one to this one, and this one to this one, then those 3 lines meet in a new point, which we'll call the Y point, or the second double point of A1, A2, A3. There's a new point Y. The natural question is, does it lie also on the orthoaxis? The answer is no. In general, it does not. Well, can we keep on going? Can we take the double triangle of the double triangle of the double triangle? Well, you can do that. And then you could ask, well, is that new triangle also perspective to the original one? And the answer is no in general. So what happens for the first double triangle and the second double triangle doesn't appear to happen for any of the higher doubled triangles. So there's a first double point, X, second double point, Y, and no more such points as far as I can tell. But I promised to tell you where this Z point came from. So you're probably thinking X, Y, well where's the Z point coming? Here's where the Z point arises. It also is a construction from the double triangle, but the double triangle together with the dual triangle of the original. Okay, so theorem is the double dual triangle perspective theorem, which says that the double triangle, which we're calling D1, D2, D3, and the dual triangle, say L1, L2, L3, of a triangle A1, A2, A3, are perspective from the Z point, or the double dual point of the triangle. So there's our original triangle A1, A2, A3. There's the double triangle D1, D2, D3. What is the dual triangle? It's the triangle obtained by taking the duals of the 3 points, or better, the duals of the 3 lines of the triangle. So the dual of this is up there, L3. The dual of this one is L1 right there. The dual of this one is somewhere down here. And that then is the dual triangle of the original triangle. And the claim is that that triangle is perspective with the double triangle. It means if you join L3 with D3, you join L1 with D1, and you join L2 down here somewhere with D2, then those 3 lines meet at a point, and that's the Z point of the triangle. The perspective between the double triangle and the dual triangle. And it turns out that this is the same Z point as in the centroid circumcenter correspondence theorem that we talked about last time. In particular, this double dual point always lies on the ortho axis. And this construction works independent of whether midpoints of the triangle exist or not. So it's a more general construction for the Z point than the previous talk. So let me close with 2 more theorems concerning cross ratios. We've now found 5 interesting points on the ortho axis of a triangle. So here's a triangle. Here happens to be its ortho axis. And here's the ortho star S, the ortho center H, this double point X, the base center B, and this double dual point Z. And one theorem we've already noted, it's a relation between Z, B, H, and S. So the ones not involving X. And Z, B, H, S form a harmonic range of points. So in other words, these 2 are harmonic conjugates of these 2, and vice versa. And here's another theorem involving the 4 points Z, B, X, and H. Those 4 points also form a harmonic range of points on the ortho axis. So amongst these 5 points here, we have 2 sort of interlaced sets of harmonic ranges of points. It's a reasonably interesting situation. Now all the constructions that we've been doing so far ultimately come down to the J function. This J function is used over and over again in this subject. We want to understand this J function now in a slightly new way, which is going to connect to our matrix point of view. In fact, it's going to connect to a very important Lie algebra in mathematics called SL2, and in a very important identity going back to Jacobi. And so the J function is what we're going to talk about next, connecting it with linear algebra. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.